planes, either in X plane, Y plane, or Z plane. Later, we'll do more about it. We'll solve how to work around it. But for now, just remember the basic things. And now we comes for kinematic chains. Kinematic chain is a fundamental structure which tells how a structure is aligned, like how a structure is there. Like if it's there are two types of kinematic chains. Like if it's open chain or closed chain. We'll go through the definition first. A kinematic chain is a fundamental structure of nearly every moving machine, serving as a skeletal system that allows mechanical motion. This concept describes an assembly of a rigid bodies connected by movable joints, which collectively constrains and guide motion in a precise way. Okay, so what this guy is telling is this rigid body structure, how a skeleton is. If you take your own skeleton, um, it's an important thing, right? How it moves. Like you can't just move your uh, elbow in 360 because there are constraints here. That's how it tells us. It tells us how it can move, how much it can rotate, those things. There are two types of open chains. Mainly, there are a few more, but there are like combinations of open and closed remaining. But two are main: open chain and closed chain. Open chain. This type of kinematic chain has at least one link which is not connected to any other link, and it is to be used to transmit motion or force between different parts of mechanical system. It means one end of the kinematic chain is grounded and another is free flowing, which can move around like this. If you see, this is a kinematic chain, open kinematic chain. This is ground, which is connected. We connected a joint to it, link, joint, link, joint, link. Now this is open end. So we call it open mechanism. Okay. These mechanisms are used everywhere in robotic arms, this one. And we have here the revolute joint. It can move around from point A to point B. Like it can't do 360 because it's floored. It's connected to a floor. But these can do a revolution. A complete, it can move 360s if unless it's hitting it. So that is open chain. And open chain mechanism, I think it's the same thing. And I'll leave it. We'll discuss about it. Then comes closed chain. Like it is connected. Both ends are connected to ground or something else. It is not a complete like a open chain. It's a closed loop. So that's what we call as um, closed chain mechanisms. Any doubt in this? Everybody good? Everyone listening, right?
Yes, sir.
Okay, let's get to another one. Now we will. This is a specific one, which is called workspace of a robot. It is specific to robot arms only. Like how where a robot arm can reach. As you know, robot arms are fixed to a certain place. Like it is either fixed to floor or ceiling or to your side walls. It is fixed somewhere, and we have to know how much it can reach. So we call it workspace. How much it can reach. See, if you see here, this is a workspace. How far it can reach. How good it can go. There are two terms we use. It first is reachable, a reachable workspace. It means the end effector. End effector in the sense, I hope I had photos, I forgot. Okay, I'll explain what end effector is. If you have a robot arm, okay, let's say just search it, robot arm. Robot arms. Let's say this one. Okay, there's the robot arm, right? Just forgot about this gripper. Without the gripper, we call it manipulator. With gripper, we call it the gripper is called end effector now. The tool which is at the end of the robot arm, that is what called a end effector. Okay, and and a reachable. This one. Huh. Reachable workspace means how far that how far that end effector can go, how many places it can reach, how many points it can reach. What we can say, those are end effector. So reachable workspace. If you Google it, any robot, any robot arm, you will have a what do you call mean specification. You will read reachability, either 1 meter or 800 mm or 500 mm. You will read like that. That means how far the robot can reach. And next is texture workspace. It means a robot arm can reach till here. Let's say let's say this arm can reach here, but when it reaches the top, it can't move completely. Okay, it can't reach every axis. Like this is a 6-degree axis robot. Now it can't do its 6-degree movements here, right? It can just reach here. That's it. It can't go down and reach top because now this is the bottom place. Those are called dexter. I'll show you a small demonstration also. I'll send you this link. You can try yourself. There's a open thing in which you can try different robot arms, how it moves, those things. Live version. Let me show you this link also. If you want to try, you can try. It does take a lot of CPU power. This one, yes. So now we are in planar robot. I want 6-degree robots. Kara, CNC, elbow robot arm. Check. This is good. So this is elbow robot arm, you said, and I think it can move in 3 degrees. Wait, let me try some other robot. It's actually big. Addition, cylinder, linear, twist robot. Not a big robot, man. The small ones. Spherical robot, let's say. Okay, this is a spherical robot now. Make it big. Spherical robot is this one, which we learned a few days back. This robot, which has a workspace of this kind of thing, like a sphere with cylinder shapes. Yes, let work on planar only then. Planar robot. It can move in one plane only. Like here, it can only move in XY. It can't go Z. Okay, this is angle 1, angle 2, angle 3, and this is our end effector here. This is our end effector. Let me move angle 1. I hope angle 1 is this one. If I move this one extreme left, now it moved from here to here. This, if I move this one, now I'll move this one. It should move here around. I hope. Moving completely. Yeah, see, now it came here. Make a sweeping motion. So that's our workspace we determine for every robot. Not like this. We have a separate MATLAB code for it to say how far it can reach, how many points it can reach, those things. So that is workspace, robot workspace.
Sir, should we try to build a simulation for ourselves that if we are given a certain robotic arm and how far it can reach in XY and Z direction? Should we build it?
I didn't get you. Like we will be building a robot arm in future, like in ROS, we'll be doing it. Not now.
I mean, I am asking for a Python analysis of if I am given a robot and how far it can reach. Should we try to build it?
I didn't get you. Can you elaborate a bit?
I mean, for our understanding, I was just asking that as a minor project from understanding this introduction to robotics, should we try to build Python or MATLAB analysis on a specific robot arm on how far it can reach?
We will be building a robot arm, but if you want to build now, you can try. Like I won't stop. Is that your thing, or you are asking how should we build?
No, the first option.
Okay. Okay. First question.
The first option.
Okay. We
Should
will
I
be
use?
building.
Okay, okay. Thank you, sir.
We will be building using ROS. Okay. So next is torque. You must have learned about torque in your 12th class, I guess. I hope 12th or 11th class. So what torque generally is? It's a rotational force. How how much rotation force it generates while rotation. For robot arm, torque is most important thing, right? Because we have open chains, and at the end here we are lifting 5 kg of payload. How much torque I need to lift that thing? Let's say here I have 10 kg for 5 kg of payload. How much torque do I need in this joint? I need to understand right now. For that, we have formulas, we have different mechanisms, uh, we have a structure to do it. Force is, the formula is simple: force plus distance. Okay, but now what happens is I want to know the weight, how much weight it has, how much different components weight, a link length weight, the weight of motors, all those things it comes. So we'll be learning that also. Just an introduction to that. And while moving, I can't just have like a 5 kg weight and just stand there. I have to move it around. The inertia also have to calculate. While moving, the forces increase, right? If I'm going to point A from point B, the force increase. For that also I have to calculate. And vibration increases. Those things. Yeah. Then comes how now I can't just have a motor which can lift 10 kgs of weight, right? Those motors will cost a lot to you. We don't do that. We have something called gearbox in your bikes, in your cars, everywhere you see a gearbox. What gearbox actually does, either it increases torque or increases speed, right? How many of you know how to drive a car? Like in while driving a car uphill, what you generally do is you go to lowest gear and drive upwards, right? Because we say pick up, it will pick up and it will go up. What generally happening is it is increasing torque, so it can sustain more, so it can pull more weight in uphill direction. So that's what torque helps us. And gearbox, and we have different types of gearbox or gear systems, we can say. We use something like gears only with using gear train is you will see normally in your cars. Gear train, we call it a set of gears set up in a line, and we have different gears, sorry, different gears. And when I shift one gear one to gear two, it will uh, go and lock in other gear, like those things. We use that. Another is pulley systems. Different pulleys we have, and depending on the or combination, torque increases. Then belt driven, not the belt you think. These are timing belts, we call timing belts or V-shaped belts. These belts you will have, uh, I don't know where you see, but like a chakki machine, atta chakki machine, you will see. Like inst- it's a V-shaped kind of belt. It will in your sewing machine you will see mostly these belts. A big wheel is below, and another wheel on top. You have a wire kind of thing which moves around. Those are belt ribbons. Next comes harmonic and cycloid. We'll learn more about this. These are these are the gearboxes we generally use in robotics. Harmonic, cyclic, and planetary gear systems. We'll learn about this more. Now comes structural design. Okay, you just can't build a robot without considering a few things, like how much rigidity it has, stiffness, toughness, or those things. We'll go one by one on all of the things, because these kind of things which ensures you how safe the robot is and how precise the robot is, and efficiency is most important, because you have multiple, like, just consider this kind of robot arm. Okay, this is a industrial robot arm. This thing, it is a 6-degree robot arm. Okay, it has 6 motors. As I say, just by motors we can't have the desired torque. So we'll add few more things, like here. Wait, I'll change it. Where is the one? Button. This one. This one. No. Robot arm. Hmm. Yeah. Here, like the first 3 joints will have something called a gearbox. The AI generator too much. This robot arm. Everywhere I see just in these one. This one here. There's a Fanuc 2000. This is the biggest robot actually. It can lift a lot. So you can see here, it's a big base. Now, a motor is small here only. We call it an AC motor. We'll have in electronics class. We'll learn about it. AC motor. That a small AC motor is rotating this big robot. To rotate it, we have different gear systems now. Gearboxes, like either we have a warm gear system or planetary gear system. Those gears, when so many parts are moving, will have a efficiency loss. So we need to consider those. Here we have gearbox one, two, three, mostly first, second, third as gearbox, and these one have belt drivens. Okay, so that is something we have to consider while planning a robot arm. So stiffness and rigidity, the ability of the robot's structure to resist deformation when load is applied. Uh, Recently, I built a robot, a SCARA robot. Okay, it will look like this one. It's a big one. It will look like this one. So what I did was, instead of using metal parts, I don't have any metal parts, so I printed everything 3D print. So now what happens is, when I apply weight more than it desired, it is made for like 100 200 grams payload. But if I put 2 kgs, even 1 kg, the whole robot, which should be in perpendicular 90 degrees, bends around 30 to 40 degrees, this much, because I'm using plastic parts now. Okay, not just here, from base to top, everything just deforms because plastic malleable, and it just bends. If I change those things to metal things, everything will be straight again, because the robot is strong. Only the connecting joints is plastic. I don't have picture. I guess, where is it? I'll show the picture later. So that's what stiffness is. See, it reduces unwanted bending links, improves repeatability. When you're moving your robot continuously, if it's not that much, 1 second, I'm getting a call. Okay, guys, sorry for that. Let's go improve repeatability. So a robot arm is not just like it will just stay at one place and just stand there, right? It does that one set of motion continuously, like pick and place. It just picks something from a conveyor belt and puts it in some other place. Every time it has to do the same thing. Now what happens is if it does doing the same thing again and again, the margin of error increases, right? Even in your small things, small scales, if you, even if you see, the margin of error increases. Like you must have using this something called 1 year calipers. You have a margin of error 0.01 mm. If you keep on using the same thing again and again, you will make some mistakes and you will have a issue with it, the precision, with the precision of it. That's what repeatability is. Remaining are same. Okay, remaining is okay. Next comes strength and load capacity. How much load a robot can withstand without deforming, right? You have to take care of tensile strength, think about tensile strength, compressive strength, and shear strength, cutting force, pushing force, pulling force, which ensures uh, the load you are carrying is safe and structure will not deform or break while moving. Like I've seen a robot which was lifting more than it weighs and it was moving at full speed, and just either it will throw it away or it will break. Like there are um, few safety also, or what do you call, safety mechanisms. Let's say this robot arm, this one. So what KUKA does is, let's say I have a gripper here at the end. This one, this looks good. That's too much. Okay, let's say this is the gripper. Okay, what happens is if the robot is meant to load, meant to carry 5 kg of weight. Okay, 5 kg is maximum, but I put at 6 kg. What will happen is the joint at which the end effector is made, this one, the robot is same like this. This end effector joint. This will just break off. It will not completely like a break, like that kind of. It will just unclip itself automatically because this is vacuum suctioned. It's placed using a vacuum kind of thing. Okay, it will just unlock itself and it will just fall down. So you don't break your robot, which will cost you around 50 to 80 lakhs. You'll just lose a gripper, either gripper or just or the load you're using, right? A much less costly mistake. That's safety thing with that. Strength and load capacity, so you have to think about that. We'll go through few dampening and vibration. When we have a lot of moving parts, we need to think about vibrations also and how you are planning to dampen it. Um, what happens is uh, when you have a moving parts, vibration creates. And what vibration actually do is it might unlock the screws you have, the tighten screws. It will slowly unscrew itself, or it will damage few critical components like a sensor, those kind of things. Let's just say somebody came. What was I saying? Um, so it will either unscrew itself and everything will collapse, or it will damage some critical components. In drones, you will see this mostly. What happens in drones is the whole frame. On top of the frame, you have something called this flight controller. Flight controller on top of your power distribution. So the controller main thing is screwed on top of a small rubber feet. Okay, those rubber feet, it will absorb all the vibrations from the motors, all the drone which is coming. At that point, we for that we use those things, and you will also like in gimbal also. If you see gimbal, when you move the gimbal up and down, it stays at one place only. It won't move with your arm, right? In drones, I'm mostly speaking, it will maintain a proper frame of it while recording a video. So vibration is a really important thing for robots, as we are like having a lot of moving parts. Should have something called a vibration. Learn about vibration and screws. When you come to screws, you have multiple types of screws, not just the basic screws you see. The lock nut screws we call, those are also good. And for big parts, something like what do you call this one? Where is this? Can't zoom in right now. They have these robots are basic lock nuts, or we have something called self-locking also. Like there are two gears kind of thing, two teeth kind of thing. It will just interlock itself. I'll show that when time comes. If you want to have a class on screws and nuts, we'll have separate class on that. There's a dampening, then comes backlash and compliance. So backlash, as I say, gearbox. Okay, so as gearbox has a lot of gears inside it, even your car gearbox. And for that, it's not an issue backlash. But let's say when I want to have a precise motion, like let's say I want my robot to move 10 centimeters, it's only point A to point B, 10 centimeters in a straight line. Okay. At that point, the precision is really important for all the gears to move it exactly when I want. But when the manufacturing happens, you can't just expect somebody to build a create a gear exactly to the point, right? That point, what happens is either it won't fit in the whole component itself, or it's too loose. So then when it's too loose, then when comes is something called backlash. Let's say gears are there. Okay, these are gears, gear teeth. Wait, it's hard. You can't see my hand that clearly. Let me show gear backlash in gear. Okay, yeah. I want to photos itself here. See, two gears are here, and when while moving, you will have a gap, small gap. Okay, no, it's not a big one, but these gears are moving hundreds of times just to reach 2 centimeters, and this gap adds up there. Every time you move 0. Arc, something it's called 0.1 arc, and you add up every time. Now it's overshoot by 10 centimeters. You just have to move 5 centimeters. Now it's move beyond it. So for that, we call something called, we have a backlash, and there is a technique in to like reduce, not reduce, to like ignore backlash. In programming, we do it. While programming also, will tell, okay, this much should be the backlash. We'll expect it. Just, or we have a special gearboxes also, like cycloid or harmonic gearbox, which just removes backlash completely. Or pretension bearings, high precision joint, which are costly. We can't just have like high grade things everywhere, right? Then we have high grade things everywhere, then the cost will increase. Torque sensors, those things. Next comes thermal effect. When things are moving things heat up, right? They produce noise, they produce heat also. How do you how do you take care of that? These are mostly comes from electronic parts, motor and electronics. Motors are mostly open air, like they are away from, sorry, they are generally in a well ventilated area, like in robot they're outside. What happens to electronics? At that time we have something called heat sinks, cooling system, we'll put a fan inside it, those things. I'm telling all these things because if when you're starting to build your own robot, you have to take care of all this. But now, if you can just buy robots which are much easy. Thermal effects. Then comes joint and bearing supports. To move a robot, see, joints and bearing support is very important. Like to align something. Okay, from, let's say, in this one, what do you call, 3D printers you have. In 3D printers, we have something like a linear guides to exactly to move it parallel to the printing bed. Uh, there we'll use linear bearings. We'll get to it better too. I'll explain much simple later. I think we have a separate section on bearings only. There I'll explain. Manufacturing and assembly. So when you build everything. You have a robot structure. You have a plan on how to build a robot. Now you're assembling it, or manufacturability. Manufacturability comes later, but first is assembly. What robots' main important thing is, you have a lot of good components in a small place now, right? They are really tricky to reach sometimes. So while building your robot itself, you have to think how you will assemble it. Can I reach once this thing is done? Okay, can I lubricate it once this thing is done? That's the important thing. Like, let's say now the robot has some issue, which is wait, I'll show you this one. Here, this one, this part. Inside this one part, you will have a lot of gears inside, which moves all these three. And how you will reach it? That's why they have multiple openings here. You have an opening here to reach this point to lubricate it, and this one also. Inside this, there's a planetary gear system inside this part. These are the motors. How you will reach it? How you will assemble it? That's something you have to remember while building. Like, you will have multiple iterations while you build, but remember those things. Those are accessibility and assembly. Now comes gear systems. I think this is the thing we did. Yeah, this is the thing we did. So what gear system actually does is, gear system are essential for mechanical components used for transmit powers, modify speed, change torque, and alter motion of direction in robotic system. I'm just reading it off. Uh, in robotic, gears are widely used for robot arms, mobile robots, actuators, actuator gearbox. There should not be actuators only. Actuator gearboxes, precision position system. So as I said, gearbox either increase your speed or decrease your speed. Sorry, increase your speed, decrease your speed, or same with torque also. It will increase or decrease. But there's a condition. Either you can increase speed and which will decrease torque, or you can increase torque and decrease speed. You can't just increase torque and increase speed. There's not no, it doesn't work like that. Because small gear turns big gear, then big gear turns small gear. Those kind of gear systems. A gear system also increase your accuracy, how accurate it is. As I said, either we can have a planetary gear which has a lot of backlash, or you can have an harmonic gear which has zero backlash. But uh, in robot arms, what important thing is how light your robot is. If your robot itself is light, then you can lift heavy payloads. right? Let's say your robot like this from here to here is around 20 kgs, and now you have to decrease your payload, right? Because the robot has to lift itself first. This one, this one thing, it has to itself first. It have to move. Forget about the payload first. You have to just move itself first. What increases weight? Mostly, it comes to gearboxes itself. Because these things are mostly hollow, just for structure or rigidity only. These are hollow. Here comes gear system on moving the robot. You have to decrease it. Okay, different gearboxes have different weight and different uh, pros and cons to it. Now we will go into those more in depth about gears. I think there are some mechanical students in here, right? They must know these things, basics of gears. Some gears we have, you will know this. First comes spur gear. Spur gear is the most common gear. You'll see everywhere these things. Straight teeth, parallel shaft, high efficiency, used for gear reduction, encoders, internal mechanism. A best thing is they are small, cheap, and accurate. Okay, but they are noisy and they are big. They are not compact at all. They are big. We use these things mostly in uh, planetary gears, budget planetary gears, not the extreme kind or the best kind, the budget ones. Now comes helical gears. These, as per gears, create noise and they're like a rigid kind of thing. When you shift from gear one to gear two, you'll have a pushback. Those things you will experience in spur gears. So what happens in helical gear is, as there are shafts connected in an angle. These are angled gears. Okay, they're in an angle. So you have smoother operations. From gear to gear contact, it will have a smooth contact. Okay, it's a good for high load. The bad thing about this is these are single gear helical. While moving, now this gear, one gear is pushing another gear downward or upwards, depending upon the angle. Okay, that's a disadvantage of it. To mitigate it, we use something called double helix. One is pushing down, another pushing up. We just have a double helix. It will just center the motion of it, force. So it doesn't move down. It's just transmitting motion in the way it is has way it's supposed to. Double helix. Any doubt till now? We covered a lot of things till now. Any doubt till now? Anything? Nothing. Okay, then we'll move and
No, sir.
yes. Okay, we'll move. Now we have something called bevel gear. We use bevel gear to like change the direction of this motion. Like I have a driving shaft in 90 degrees. Now I have to move it to the send it to 90 degrees. This is my driving shaft. This is my driven shaft. How will I do it? This is how I do it. This is the shaft which is in an angled, which sends the driving. There's the driven. It will move like this now. If I move this, will also rotate. This bevel thing we call. Next is worm gear. Yeah, I want. This is also similar to what should I say? A right angle only. It's a right angle gear we call. We use this mostly in robot arms for base of it, for the base. If you see this one base, if I want to move the base completely right, I can't put a motor somewhere. I can use a worm gear there. One thing which will move from a side, it will completely rotate it smoothly. But here, I guess I don't know which one he used here. Can't tell. This one. It looks like a worm gear system only. I can't tell just by looking sometimes. Okay, that is worm gear. These produce really less noise though. It's not like they are also accurate. They have good thing. No cons. Okay. Their effect less effective, generates a lot of heat. Common servo gearboxes. Servo gearboxes. I've used those. Okay, these are the basic gear systems now. Spur gear, spur gear, and helical gear are gears. Then comes the and these two are also gears. Now we learn about something like a combination of gears. Like different gears are there. We learn about gear systems now, gearboxes. We'll just do this one and we'll end the class. Let me wait a minute. Planetary gear thing. Okay. Now planetary gear. This is the gearbox. So what happens is now I want to increase or decrease my torque. Okay, and I need it. I need to be done in a compact way. I can use a gear train. Multiple gears are aligned in a line formation. I can try that, but or that will increase space and weight also. I can use a gear system, the gearbox system. The first one comes as planetary gear. Okay, first I'll show you how it moves. Let it load. It's loading. Let it load for a while. Okay, we have first a sun gear. In center, we have a sun gear. This is connected to your motor. Okay, this one. Once this thing load, I'll show you properly. This center gear is connected to your motor. What happened? I move it. And these are planet gears. There are planets which are connected to your shaft gear, the sun gear. Once the sun gear moves, it will rotate this planet gears also. These planet gear rotate your ring gear. Okay, got it. Then whole system moves around it. The next system, let's say, loaded. Yes, good. There's the motion. Okay, yeah. Just remove this one. That is like this one. Okay, this is the sun gear. I have a shaft here. I'll connect a shaft. Let's say this is the shaft which I connected. I'll rotate this one. This will rotate this thing, which will indeed rotate this one's also, like a mechanism complete. Let's say if this one rotates two full rotation, that this will rotate only half. So two in one, and these gears are connected to another shaft, the driven shaft, like mechanism go on, and this will rotate then. That's how a planetary gear moves. I'll show a small video of it to better understand this thing. Planetary gear system, backlash gears system. There are many videos. Any video you can see. Yeah. Here. See, like this, it will move. There's a planetary gear. I can change the input also. If I don't want to move this one, I can move this one. I can move this one. There are multiple inputs I can give. We use it in robot arms. These are generally used in robotics everywhere. Robot arms, cobots. There. Then we have harmonic gear. Okay, what harmonic gear is? This gear has zero backlash and really high reduction ratio, like 2 to 50. Only two rotation will give me 50 times the effect of it. Those things, and highly repeatable. The bad thing about it is it's costly, and we have something called the parts for it are not very cheap. that durable. Okay, now, and we have a thin gear here. We call it a spline. Okay, this is a thin gear. If it when it moves around, if you just let me make it big. Just concentrate on this one thing. See how slow it moving. This just the driving gear, the driving it is in a cam kind of shape. If you do know the cam shape, like a elliptical. Okay, it's an elliptical shape, and that thing is driving the whole mechanism slowly. You understand how it works actually? This one, this one also the same thing. It moves one by one slowly, interlocking with each and every gear. Inside we call it a spline, and it is connected to a big shaft. When it rotates slowly, it flexes the spline slowly. It is a rigid. It has really less zero backlash because you can't. It's completely interlocking with it and removing it and going to the next step. Each and every gear is connecting every time, and the cons of it is spline uh, has less work hours. It can't go forever. It generally breaks. And another thing is these gearboxes are really costly. You will see this thing in high-end robot arms like a UR5 or Kuka's robot. You will see this gearbox there only. But these are mainly used in cobots because if you see cobots, they are really silent and you can you have something called back drivability. Like you can just hold the robot and move it around without any issue. Okay, exoskeleton. Then comes cyclode drive. This is a drive box, a drive gear. Better to show you this time. This is the hardest to explain, I would say, for me. Let it load. Yes, here. Let me explain the parts first. We have outer things are called fixed pins, fixed ring pins. Inner is disc pins. Yeah, wait, let me just show you first how it moves. Okay, this one. This is our driving shaft. The purple one is the driving shaft, and it see how it moves. If you see it, it is also similar to your what do you call cyclo harmonic gear. But here we have something called an eccentric shaft. This one. See, this is my shaft, and the shaft is connected to connected to offset. It's not in the center exactly. It's connected off a bit of offset, which helps me obtain this rotation like this, not in the center, just bit offset. These are the second best compare after harmonic gearbox, but these are big and bit of heavy. It takes a lot of different parts. You have base plate here, you have bushings, you have bearings, multiple bearings inside it. Just to make this one small thing, you have a lot of parts going inside it. That's why these are heavier, slightly heavier, and complex manufactured. There are a lot of parts, right? Not just one thing. You have your mecentric shaft, you have your multiple bearings, you have multiple discs, and your multiple bushings you have. But these are also good for robot arms and high shock resistance. You can take a bat and hit it, and it will stay in one place only because they are like properly locked in its positions. That how good they are. Okay, any doubt? We'll end the class today here. Any doubt till now? Anything you understand about gears and system? Tomorrow we'll learn about gear ratios, backlash, efficiency, center of mass, those things. And I'll also make a few videos for this for you to understand it. Okay. Any doubt? Anything? All good?
Sir, I wanted to ask that it is there are many types of gears, and
Yes,
so
there's
will you
many.
be sharing this PPT to us so that we can go through all the topics, or we can tell us some book so that we can see each topic in detail somewhere.
Book I can't tell because these are made one by one. I just made them. I didn't refer to books. Later, I think I'll give you the PPT. Okay, I'll share it with the group.
Okay, thank you, sir.
Okay. Any other doubts? Everybody understand everything today?
Sir, can we get the PPTs from the last class and today's class in the
Yeah,
group?
same. Everything is in one only. I'll I'll share it.
Thank you, sir.
Sure. Akhil, are you outside?
Yeah, sir.
Okay, guys. Like be in front of your laptop, man, or compute, or have a notes. Just go. Don't roam around. I'm also busy. I'm just taking class today for you people. If you respect my time, I'll respect your time also, right? That's why. Won't be like that next time. Yes, yes, one turned off. Okay, on now. Okay, then we'll meet tomorrow. I'll share this thing with you. Okay, guys. Bye. Have a great night.
Thank you,
Thank you,
sir.
sir.
Thank you.